Okay, so everybody got, there's mass spec notes, there's the mass spec homework, and then there's the NMR notes, so we're going to start on today. So where we were last week was we talked a little bit sort of briefly about the technique of mass spectrometry. So what was the big thing in mass spectrometry from last week?
There is a stream of electrons that are pumped at the particle that's moving by the fragment to get to multiple different components for passing.
Okay, so first thing I've got to do is I've got to hit the molecule with an electron beam to kick out an electron and put a charge on it. And the first molecule is going to be the plus dot, the radical cation. And then that radical cation is going to do what? It's going to break apart into fragments. That's what we're going to talk about today. In terms of these peaks, we'll just lay out the terminology here. So if I was to look at methane, CH4, so CH4 has had an electron beam hit it, kick out an electron, so now I have a CH4 dot plus. That's basically it's called my molecular ion. So it's an M dot plus, or M plus dot. So that's the intact molecule. The intact molecule is always going to be the peak farthest to the right, the highest mass. And then where did this peak at 17 come from?
Carbon 13.
So that's a methane with a carbon, not 12, but a carbon 13 isotope. So that peak would be called the M plus 1 plus dot. So that's with an additional mass of 1, which comes about because that molecule is now the carbon 13 methane. And then in the next slide, if we look at the isotope percentages, carbon 13 is 1.1%, and so that carbon 13 isotope, that peak would be 1.1% of the CH4 being carbon 12. And then everything else is a fragment. So what we're going to look today is we're going to go through functional group by functional group and look at how the molecules fragment. Now, that's important if we wanted to determine the individual fragments in the mass spec, which you can do, and you can piece the structure back together again. Each one of these is a piece of this, and so if you're just going to use mass spectrometry to figure out a molecule, you'd have to know what all those pieces are and then try and put them together. We're not going to get that detailed. My primary goal is as we go through these different fragmentation patterns, I'm going to focus on carbocations and radical stability. So it's going to help reinforce what we learned in lecture and what we hopefully have learned in lecture, even from last semester, even from like resonance structures in the first couple of weeks of classes of last semester. So we'll actually go way back or try. So that M plus 1 peak then, this is the isotope table from last time, so that we can say, okay, carbon 13 is 1.1%, and then of the carbon 12 peak, which would be 98.9% of the carbon, we're not going to see carbon 14. And we're going to see these percentages of the different nuclei unless we've isotopically enriched them. So it is possible, for instance, well, one of the things that's commonly done sometimes is that you can, if you're going to like grow media or grow something in a petri dish, if you feed it carbon 13 enriched and nitrogen-15 enriched froth, it'll incorporate the carbon-13 and nitrogen-15 into whatever whatever it's making. So you can actually make enriched proteins in carbon-13 and N15 by feeding them what's called a labeled media. But we're basically going to limit ourselves to natural abundance. Okay, so we're not going to see much deuterium unless it's been enriched in deuterium. All right, so how do molecules fragment? Let's say I have a molecule A, B. And so it's going to fragment into two parts, part A and part B. The way the molecule fragments is going to be so that one part is a radical and the other part is a carbocation. So if I take my AB, my molecule, it's made up of part A and B, hit it with the electron beam so it's now a radical cation, I can break this apart into two different components. It could break apart into the A plus B dot, or it could fragment into A dot plus B plus. So in other words, when I fragment a molecule, which means I'm going to break a bond. When I break that bond, one part's going to be the carbocation in one case and the radical in the other. So I actually form these two sets of radicals and cations. Now the problem is that the radicals have no charge. And in mass spectrometry, any molecule that doesn't have a charge smashes into the side of the container, or the side of the mass spec. Only the molecules that have a charge can be moved by the magnetic field to the detector. So neutral molecules that are made or radicals are not detected. Only the carbocations are. Oops. So only the radicals we don't care about. So if I'm going to fragment a molecule, what am I going to see? Am I going to see more A plus, or am I going to see more B plus? Am I going to see more of the A carbocation or the B carbocation? It depends. Which one's more stable? So I might see both of them, but I'm going to see a bigger peak in the mass spectrometer at the mass of the more stable carbocation. So whichever one of these, whichever the great one with the, let's call it the greater abundance, or the larger peak, that's going to say that carbocation is going to be the one that is more stable. Because what we're going to do is we're going to look at different possible fragments this afternoon, and then I'm going to say, okay, we know the mass, we know which mass is more abundant from the mass spectrum, and so what does that correspond to? And it's going to correspond to the more stable structure. And then we're going to have to talk about, well, why is that more stable? Okay, so this is what happens. The rules for mass spectrometry as far as carbocations go is different than lecture. Right? Lecture, you lose points, maybe lots, maybe a few, if you write primary carbocations. Usually it's just an X through it with a, oh no, a primary carbocation exclamation point. That's how I do it. Try and use a little humor to keep my sanity. There's not enough humor right now to keep my sanity. Again, I'm just saying that. Don't worry about my mental health. Dr. Weiner said, well, how do you know you're not losing it? I'm pretty good at self-evaluation, so I think I would know when I'm losing it. Then again, that's not always the case. So far so good. So we need to figure out which of those two. It'll fragment to form the more stable carbocation. So what we're going to do is talk about why. That's going to be the focus of this in the context of the mass spectrometry. Okay, so that's how we fragment. And so I'll just sometimes just go right to writing both carbocations, both fragment carbocations. But remember, they're not going to be formed equally. And this set is here, the other set, but we're just not looking at the dots. The radicals smash into the side, and they're never detected. Okay. So let's take a look at a couple of alkanes. So we've got nonane, and we've got 3-methylpentane. Now, in these mass spectra that I've given you, and these include the ones in the homework, these are taken from the instrument next door, the $200,000 data, or 200, not that much, 102,000 compound database. And so I can go in and I can pull up any molecule I want that's in the database. The little triangle tells me what the molecular weight is. So that triangle is telling you what the M dot plus peak is. And what you can see is that that's generally small compared to the fragment peaks. So it's not like methane where it was the biggest peak. Sometimes it's small, sometimes you can't even see it, which will be the next case. So then that means that nonane equals its molecular weight is equal to 128 atomic mass units. Technically, the x-axis is the mass to charge ratio, but since the charge is +1, it's simply the mass. If we do biomolecular mass spectrometry, sometimes molecules can have a +2 or a +3 charge, and that just complicates everything. Because then when you get a number, is it ×1, is it ×2, or is it ×3? But in our system, since we're doing small molecules, only +1. Okay? So we can start to think about, okay, what about these fragments? And we can think about them from two ways. Let's say the peak at 99. We could say, well, what is that peak at 99? I could try and take this structure and figure out what bond to break so that it adds up to 99. Sometimes that works well. Another strategy might be to say, of the 128 of the intact molecule, what fragment am I losing to get me to 99? So I would take 128 and subtract 99 from it, and I would get a mass of 29. Good, that's what I was thinking. Somebody has to have their job today to check my math at all times. So yes, we would lose 29. So then we have to think of, okay, what carbon fragment would weigh 29? So we're going to be doing a lot of simple addition this afternoon. And you will when you do the homework problems. So if we think about that, well, carbon weighs 12 each. So the maximum number of carbons that I can have to get to 29 without going over, right, like the Price is Right, is 2. So 2 carbons would take me to 24, and that means that I would have 5 carbons left. So if I wanted to make a fragment that weighs 29, it's going to be C2H5. Now, what is a C2H5 fragment? It's going to be a CH2 and a CH3. And so what's happening in this system? Well, the intact nonane is fragmenting on that bond right there, and I'm losing the CH2CH3 at the end of the molecule. And you could say, can you do that on the other side of the molecule? Sure, it's fair. For other molecules, if you lose a CH2CH3, maybe there's 3 different methyl groups, or 3 different ethyl groups. Well, what's going to dictate that? What you're left with. Because the thing that you're going to be left with is usually going to be the most stable carbocation. So if I lose a CH2CH3 dot, that means what's left over here is a C7H whatever plus one, the carbocation. Okay, so right there I violated lecture rules by writing a primary carbocation. In the gas phase, high energy environment of mass spectrometry, primary carbocations are okay. Are they as stable as a secondary? No way. But they're at least allowed to be written. So I can do that. And I could go on down the line here. I could say, well, how do I go from 99 to 85? I'm going to lose another 14. What corresponds to 14? CH2. So now going from here to here means I lost another CH2. So overall going from 120, 128 to 85 means that I lost an ethyl group, a propyl group. So this is one way we can determine what the fragments are by figuring out what mass I'm losing and then putting that mass into the fragment. So that means if the minus 29 here, if the peak at 99 was cleaving that bond, now cleaving this bond gives me the 85 fragment left over. And then what you can see here is that 85 to 71, I just lost another carbon. 71 to 57, I just lost another CH2. Then 57 to 43, I lost another CH2. Now, what are the 2 biggest peaks in the spectrum? 43 and 57. Does anybody have any kind of thought as to why those 2 would be the biggest? Why they would be the biggest fragments?
Stop cleaving at this point.
It is definitely stopped cleaving at that point. However, now the other pieces we're going to see are the smaller ones down here. So 43 minus another 14 would be 29. 29 minus 14 would be 15. 15 would be a methyl carbocation. It's the least stable of all. But 43 and 57, in terms of where is the cleavage happening in that 9-carbon chain, in the middle. So what's happening, why those 2 peaks are the biggest, is because that's where the molecule is basically being cut in half. So if you think about it, if I cut it in half, probably between 4 and 5 carbons, there's not much difference in stability of the carbocation, so that's going to make those 2 peaks the most abundant. So there's also some statistics involved here. Molecules like to kind of be cut in half. Because when you cut them in half, no matter which way you fragment them, you get nearly the same carbocation. And sometimes we put a lot of stock into those those are sometimes called, I think, the parent fragments. Or the parent ions, the ones that are the biggest. If I'm doing computer matching and I have 2 spectra and the parent ions, the largest ones, aren't at the same mass, I immediately say that's not matched. And I would even be tedious enough that if I'm looking by hand at matching, if 43 is supposed to be higher than 57, and my structure I'm trying to match it with, the spectrum has it opposite, it's not a match. Okay? So there is some symmetry elements here. Molecules like to be cleaved down the middle. And there's a statistical one as well. So what we could take away from this is, we'd probably take away that if we took statistics out of this, that the 4 and the 5 carbon, or the 3 and the 4 carbon chains are the ones that are probably the most stable. So it's cleaving, I'll modify it, cleaving near the middle, not exactly the middle. 9 carbons cleaved at 4 would be 57. 9 carbons cleaved at 5 would be 60 something, which there isn't a whole lot of. So that's kind of how we look at a mass spec. And we would need to look at that level of, that we'd have to be that tedious to look at every fragment if this is all I got. If this is how I'm going to put the structure back together again and figure out what my original molecule is, that's it. That's the only way to do it. Fortunately for us, we're going to have NMR and other things that are going to be helpful. Okay, so that 3-methylpentane. Let's see, what do I have? Ask students to identify 71 and 57. So could you figure out what fragment, or I'll even take what fragment is lost, that'll give you the 57 and the 71. So I'll give you a couple minutes. And then I can randomly call on somebody. I could if I had everybody's name in the wheel, in the spinning wheel, which I don't have now, but I could put everybody in there now so that I'm ready to do that. So what would the fragment, or what needs to be lost to form the 71? And then what fragment needs to be lost to get me to 57? Okay, so what's the peak at 71? Josh?
The fragment that popped off was the methyl group at the 3 position. It's to make a secondary carbocation.
Okay, so we're breaking this bond, and the peak, and it weighs 71 would be that secondary carbocation.
It also has the N pop-off, but more stable versions, but the other one is.
Okay, let's hold on for a second there. So if I lose this methyl group, that's going to give me a secondary carbocation. And so 86 minus 15 gives me the 71 because I've lost the methyl group, so I've lost 15 AMUs. If I lose a methyl group on either end, what kind of carbocation am I going to get? A primary, so this is probably the preferred structure. That's the most stable carbocation that weighs 71. Right? There's a lot in the homeworks. Some questions say write the most stable carbocation. So you're going to have to look for the most stable, tertiary more stable than secondary, more stable than primary.
But if you don't tell us, it's always preferred for being uniform stable.
I don't. Yeah. Consider that to be the rule. And I didn't make the rule. Whoever decided that secondary carbocations are more stable than primary is made the rule. Maybe chaos, maybe some supreme. I don't know. That's over there. That's a But that's the rule of nature that will always be the case. So secondary, the most stable carbocation will be the one that's more abundant. All right, so the 71 then, that's the one that weighs 71. How about the 57? So cut off one of the side ethyl groups, maybe like this one. And so that's going to make me lose 29. And so the 57 would be, again, a secondary carbocation. Now, how many ways are there to make that carbocation? I can do 2 fragments and get the same carbocation. So that's going to play a role in the abundance as well. But statistically, there's 2 ways to make that. So that's for alkanes. We're always going to see fragments of ethyl groups or methyl groups or propyl groups. And so it's going to be pretty boring. And the most stable carbocations are going to be, the secondaries, tertiaries. The primaries will always be there, it's just they won't be as abundant. What fragmented to make 56? Let's see if I have that in my teacher notes. I spent the break writing up these teacher notes primarily for me, but also for Dr. Simmons. And when she came in, she's like, I spent the break going through this myself, figuring it out. If you knew how old you were, how old she got her PhD at 6. So she's very spry, and that's amazing. She's like, what is the 56 peak? Well, that's a good question. We know we lost the hydrogen, right? So let's just say, for the sake of argument, that I've got a plus charge here, and I don't know. This whole thing then is a plus dot. The easiest way for me to have lost a hydrogen is to somehow put a double bond there. So but it's got a plus dot associated with it. So if the same way, let's say I had this molecule, and I said I'm going to fragment that with my electron beam to form a dot plus. If I lose a hydrogen, I can end up with a double bond here being a dot plus. So I know you're like, if you easily extend it, get rid of a plus charge. So that's most likely what it would be. Something along those lines. This is 57. That's right. Am I correct on that? So that's 4 carbons, which is 48. Plus that would be 9 more hydrogens. So if I'm drawing this, I've got 1, 2, 3, 4. So that's 48. And I'll mess that up at least once this afternoon. But it's 48 plus then 3. Because there was only, when I broke that bond, here there was only 1 hydrogen there, so that's 3, 4, 5, 6, plus 3 more. Yeah, or I could have written the other side with the plus charge, or I could have written the other side with the plus charge. And we're not going to necessarily get into all the minutia here, because that's one of the questions, how you read it. And so that's going to be the main one. So that's alkanes, functional group number 1. How many more do we have left? Alcohols. Alcohols are the easiest because their main fragmentation pattern is that they lose water. So they lose a neutral molecule. So here is butanol, and butanol weighs 74. So I know it weighs 74, and you can barely see the mass. You can barely see the molecular ion, which is the intact molecule. So you can barely see that. Because what happens? Because what happens is that when I have the OH with the plus dot, how am I going to eliminate water? Just like we do in class. I'm going to take a pair of electrons here, that's going to leave, so I'm going to lose a neutral molecule. So I lost 18. And I'm left with 6. The most difficult part of the mass spectrometry, honestly, is you have to remember that there's always either a plus or a plus dot in the molecule. So I literally am losing a neutral water molecule and going from plus dot to plus dot. It's not necessarily a fragmentation. Now, if I had this double bond right here, I could fragment it, which would take me down into this messy area. With the thoughts that there could be a hydrogen, there might not be a hydrogen. We're going to ignore that for the moment. So when you're doing mass spectrometry of alcohols, the molecular ion is really difficult to see. So you might have the question, well, if the molecular ion is difficult to see, how do you know that you're getting the right molecular weight? That requires that you know ahead of time that you have an alcohol. So before I put my sample into the mass spectrometer, I need to know that it's an alcohol. How am I going to do that? Again? Question? Yes, maybe. There's a more definitive way. But nothing much is going to happen if I have mass. If I had a chunk of sodium metal, it'll fizz. But there's an even more definitive way. What did we do last week? Use infrared. I said last week, and I know it was last week, but infrared, mass spec, there could be complementary techniques. That's what I mean. From the infrared, I have an alcohol. That means when I put in the mass spectrometer, I know that I'm going to barely be able to see the molecular ion. So I'm going to make some assumptions that whatever my farthest peak to the right is, I'm going to add 18 onto it. Because I know I lost 18. Because that's what alcohols do in mass spectrometry. So without infrared, we would have a very difficult time knowing this. If I just knew I had an authentic alcohol, then I would also know. So that's where infrared comes into play. It could give us a screen of what functional groups I'm already in. So if it's an alcohol, I'm going to know that phenomenon happens. And I'm going to watch out for it. Does that make sense? Okay? Out of curiosity, write, what do I have here? I probably have, ask students, how does 136 peak form? 153 minus 136 is? Actually, sorry, 154 is the molecular ion. So 154 minus 136 is 18. So what's the 136 look like? So you're going to do what I just did. Use water. From hydrogen from the beta carbon to the alpha carbon of the OH. Structure. So I'm always going to lose the water from the OH and the carbon that is basically the beta carbon. We're going to lose like a beta hydrogen. Right? That's the one you see. Carbon is the one that we lose. Carbon is the beta carbon. No? Okay. The carbon with the OH is called the alpha carbon, and then in this case there's two carbons attached to that, and they're called the beta carbon. So when you lose your hydrogen, you're going to lose one of the hydrogens that's attached to the beta carbon. And if I use terminology like that, it doesn't make sense. You should handle saying that's how we determine what double bond goes to be. All right. Yes. Would there be 3 beta carbons? Well, you want to call that a beta carbon? You can, but actually we don't lose the hydrogen that's attached to the double bond. That hydrogen can't really pop off. It's not very difficult. So that one, that beta hydrogen, I'm going to eliminate because we've never done that in the past. So if I'm going to lose an HOH, I'm either going to lose HA or HB. HB? How many people say HB is the one with the biggest loss? HA? Nobody wants to go for HA? Why HB? The most substituted double bond, which is the most stable. So when we lose the hydrogen, we're going to form the most substituted double bond. So we have 2 choices. We can either put the double bond there, or we can put the double bond there, and that one's going to be more stable because it is the most substituted. Okay. So that's how alcohols always lose HOH. Just like in lecture, we talk about losing the H and the leader group with the alpha and the beta carbon, and you're going to form the double bond that's most stable. Right? See how much too much lecture stuff we reviewed here. I would not go into this much detail except that it is really helpful to reinforce what we have and will learn in lecture. So there's always a method to madness. You may not think so, but there is. There's always a reason for that. All right, so again, have to take an IR to know that there's an OH in there, to know that the 136 is not the molecular ion. 136 plus 18 is. Okay. Alkene fragmentation patterns. So in order to do alkene fragmentation patterns, we have to know what their preferential point of cleavage is. And they like to form allylic carbocations. So, what's an allylic carbocation? There's an example of an allylic carbocation. It's one where the plus charge is attached to the double bond. Or sorry, on the carbon next. Wait, I just drew a primary carbocation that you would be allowed to draw in lecture. Why? Because it's got another resonance structure. So if I take this pair of electrons and move it over here, then, oops, there's a second resonance structure, so it's more than a primary carbocation. It's allylic, and so it is stable because of the resonance structure. Now, primary allylic, not as stable as a secondary allylic, not as stable as a tertiary allylic. So, those rules are still in effect. So when we look at an alkene, we say, okay, how's it going to fragment? It's going to fragment to give me an allylic carbocation. So for instance, in this one, whatever it is, 1 hexene, it weighs 84. 84 going to 69 means that I just lost 15, so that's the cleavage of the methyl group on the end. Then going 86 to 56, or 84 to 56 is what? Actually, 84 to 57 is. No, I want another 4. So 55. So 84 to 15 is 20. That's a lot. So in this case, one of my major cleavages is going to be right there. That's going to be my major point of cleavage. And this time I'm actually going to write both carbocations that I would get. So I would get that from the left-hand side, and what would I get from the right-hand side? I would get that one. Remember, the cleavage, we get both cation, radical, both sets, and I'm going to eliminate that. So what does the allylic carbon weigh? Well, this is what? This is C3, 1, 2, 3, then I've got 1, 2, 3, and then 4, 5 since I cleaved that, so that's a C3H5. So that's 36 plus 5, that's the 41 peak. Right there. The peak at the methyl peak here, or the propyl group, is a C3H 1, 2, 3, 4, 5, 6, 7. because it's got those two, and so that's a C3H7, which is 36 plus 7 is 43, so it's that one. So that's 41.
That carbocation also one.
Yeah, except we can't add. We can't add fragments. We can only break up fragments. So we can never add mass to a fragment. We can only look at them.
What about if that's the isotope?
Yeah, it could. It might be. But we'd have to check that. That would be a good one. Could be. I thought you were going to ask me more. I'd like to ignore 56. Although I probably have opened Pandora's box by saying what 56 should be. You might say, what if I cleave one carbon atom and I make that carbocation? What is that? Let's see. So that's going to be a C4, which is 48, plus 1, 2, 3, 4, 5, 6, 7. Well, at least that's the 55. So when I cleave it here, it's going to give me CH3, 2, 4, 5, 6, 7. That gives me 50. Stable? Stable carbocation? Not the most stable, but I'm in a high energy environment. So what could I do? How about I do this? What if I do a carbocation rearrangement and slide that hydrogen over to the primary position? We just talked about rearrangement. So, similar process. The rule for a carbocation rearrangement to occur is you must form a more stable carbocation. So if I slide that hydrogen over, what am I forming? I'm now forming a secondary and alkyl. So valid hydrogen shift? Yes. I'm in a high energy environment, so it will go. It's just a question of speed. In the mass spectrometer, we're talking about that being probably a femtosecond with more than enough time for these things. So that would be the 55. Didn't answer the 56. Let's see if I have 56 in my notes. I blew off 56. So I'm gonna blow it off. Because I can't just add a hydrogen. That's not allowed. There is a way we can add hydrogen atoms. We can add H pluses to molecules, but maybe we'll talk about that later. Alright, so there's the 55. My goal here is not to interpret Evans. My goal here is to reinforce some of the things that we've learned about carbon. What did we do here? We introduced the idea of allylic, if you haven't seen that before. I have the deja vu sense that we've seen it, and we saw it last semester. But that just might be. Hydrogen shifts can occur to make more stable carbon. And a hydrogen shift isn't going to change what. Okay? So, let's. It's not very quick enough. Let's take a 7-minute break here, and then we'll go ahead and finish. And go through it and try to finish this off. If we need one more break, we'll get one more break. We will definitely get one more break. Okay. Now, the previous slide said that when you do fragmentation of alkenes, and this would be true for alkynes as well, right? The allylic position isn't the allylic position with a triple bond, but if the plus charge is next to the triple bond, you also get a resonance structure formed as well. It also said that you could end up with a retro-Diels-Alder reaction. And I don't think we've done Diels-Alder yet. Well, that's our first experiment in now 3 weeks. So we're inching closer. So what's a Diels-Alder reaction? Diels-Alder reaction is when we take what's called a diene, and what we would actually call a conjugated diene. So one of the things I should probably introduce at this point is the idea that when you have a double, single, double bond, that's what's called conjugated. If you have a double and then 2 single bonds in between it, that's unconjugated. So this is a conjugated system. And the importance of a conjugated system is that when the double bonds are separated by one and only one single bond, they are more stable. So this conjugated system of double, single, double is much more stable than if it was double, 2 singles, and then a double bond. In that case, the double bonds would be completely isolated from each other. But in this case, we're going to find out when we add HCl to this that we end up with 2 products, and one of the products initially won't make sense. But it will. Eventually. So we take a diene, and we add to it an alkene. The alkene is also called the dienophile sometimes. Right? The phile meaning love, so that loves the diene. And what happens with a Diels-Alder is that we have this pair of electrons move. Well, let me put my numbers in. So I number 1, 2, 3, 4 on the diene, and then carbons 5 and 6 on the alkene. So the carbon 1, carbon 2 double bond breaks to form the carbon 1, carbon 5 single bond. The carbon 3, carbon 4 bond breaks to form the carbon 2, carbon 3 bond, and now double bond. And then the 5-6 double bond is used to form the 6-4 single bond. So what we're going to make is we're going to make a 6-membered ring with a double bond between carbons 2 and 3. So if you started talking about like Grignard reactions in lecture, let you know. like what you're going to find is a Grignard reaction of the great way to make a carbon-carbon single bond. And what I said about that, whenever you can form a carbon-carbon single bond, that's important. You have the reaction named after you, you win Nobel Prizes. That reaction forms a ring, 2 carbon-carbon single bonds. So Diels and Alder, Otto Diels and Kurt Alder, they came up with this reaction. I think if I read on the elevator correctly yesterday at this day of chemistry, Alder was the student of Otto Diels. Alder's one of the first well-known American organic chemists. Because organic chemistry is not an American science. It was developed in China. So Diels and Alder came up with this reaction. 2 single bonds, a ring. Everybody has to know their name and Nobel Prize. So this allows us to make 6 Nobel rings. Now, did they create this reaction? No. Plants have been doing this reaction. When we get to this, plants have been doing this reaction for as long as they've been. So they do the Alder reaction all the time, but they don't get it. So what's a retro Diels-Alder reaction? So when you have this cyclohexene molecule, and you're going to split it up into its 2 fragments, it's going to be these 2 fragments. So again, one, probably a dot plus for each of these. So when we look at that, what does the diene part weigh? What does the double bond weigh? If we have the diene as a plus dot species, or as the plus species, then that's a C4 fragment with 2 C4, so that's 48 plus 49, 50, 51, 52, 54. So the 54 fragment in this is the diene. And then if you look at the alkene will be a C2, so that's 12, 24, 25, 26, 27, minus 1. So that fragment actually is going to be lost as a neutral. And you don't see formation of that carbon at all. That's just how it must be. So that can happen as well. You might say, how do you lose 15 out of this molecule? Because we're going from 60 here to 82 to 67. So somehow it lost the CH3. There's no CH3 for it. So we could become creative. Let's see, how was I creative? I was creative enough to say, I'm going to lose that. I'm going to break those 2 bonds, and I'm going to lose a CH2, which is a 14 fragment. So that's going to form basically this. I'm going to definitely have the carbocation at the allylic position, and then maybe the radical would be like there. I still gotta lose a hydrogen atom. And so my creative way of solving that is to say, if I lose that hydrogen atom, I've now lost a grand total of 15, and now these two radicals could pair up so that the fragment could look something like this. And that would give me an alkene carbocation plus an You don't have to do that. Usually when we lose 15, it's just enough of the time at the end. No nothing. So that's good. So that's that. But the most important thing with alkenes is form that allylic carbocation. So you want to either form that allylic carbocation. Okay. All right. So a foreshadowing of things to come. When you have a benzene ring, an alkyl benzene ring, it likes to cleave to give you this, which is not necessarily allylic. It gets a new name, that this is a benzylic carbocation. I could write 3 more resonance structures if I move the plus charge in the ring. So that's a benzylic carbocation. It's fairly stable. Now, we are going to learn later that the molecule on the right is called a tropylium ion. Don't worry. And what happens is by what's called a ring expansion, the 6-membered ring changes into a 7-membered ring with 3 double bonds in the plate. Now, when we talk about benzene, we're going to talk about it being aromatic. Aromatic means 2 things. Aromatic means it smells like something. Mothballs are aromatic. So they have that aromatic smell because they're actually 2 benzene rings stuck together. Or you could have parabechlorobenzene, which is also possible. That smells sort of mothball. Supposed to keep them on. I can open my closet and the whole flock of moths never come out, but this is a problem. Okay. So we use mothballs. You go to dollar store and get all the mothballs. Benzylic, so the benzylic carbocation opens up the tropylium. The other way to define aromatic is non-reactive or superstable. So we're going to learn that benzene ring is superstable. We're going to learn that tropylium is also aromatic as a cation, and it will not do things that normal cations do. It's actually a very stable carbocation because it has a bunch of resonance structures that you could draw, that you will draw in the homework problems, sort of like we did for the allylic carbocation. So what happens is, in the mass spectrometer, it doesn't matter whether it's a benzylic carbocation or tropylium carbocation, it has a mass of 7 or 90. And I made the mistake in class a few years ago trying to start to figure out the mechanism of going from benzylic to tropylium. After class, when I didn't get anywhere, I embarrassed myself, I looked it up, it's not true. Which means I don't think anybody knows that's how it happens. So, Doesn't matter, it's 91. How's this important? Well, if you think you have an allylic benzene, you better see a peak in your mass spectrum at 91. If you see a peak in your spectrum at 91, that means you have an alkyl benzene. And it doesn't matter if it was 3 carbons or 100 carbons. It's going to cleave to form that benzoyl carbocation with benzoyl carbocation. So 91 is a critical one for looking at aromatic compounds, because it will tell you it's aromatic. Sorry, it'll tell you it's alkyl benzene. So that one, I'm going to ask you to write the resonance structures. So that's aromatic. That's the alkyl aromatics. So the last kind of group of fragmentation patterns we're going to look at involve heteroatoms. Oxygen, nitrogen, halogen, sulfur. And so these molecules have a very specific place where they like to fragment. This is a ketone. It says it undergoes alpha cleavage. And that's where it favors. Now, before I get to what is alpha cleavage, we have to define what's the alpha carbon. Because it's slightly different than it is with the alpha beta carbons that we talked about with elimination. Which for years I didn't even talk about alpha beta carbons with elimination, but then I got tired of saying the hydrogen next to the carbon next to the carbon with the leading group, which is beta hydrogen. So I just bit the bullet and said I'll redefine it later. So in this case, the alpha carbon is the carbon attached to the carbonyl. That's the alpha carbon. And then any carbon after that is a beta carbon. We'll use this later on because we're actually going to take that hydrogen off of that alpha carbon and make what's called an enolate molecule. So all the action happens at an alpha carbon in a ketone, an aldehyde, in a carbonyl. So what's alpha cleavage? Alpha cleavage is when you cleave between the carbonyl and the alpha carbon. And so what do you make? You make that. And at first look, that looks kind of weird, because we haven't really seen anything like that so far. Is it stable? It better be, because we're going to spend a lot of time talking about it. So how is it stable? Well, let's write a resonance structure for it. So to write the resonance structure, what should I do? I'll take this lone pair and I'll put it there. I'll form now a triple bond between the carbon and the oxygen. And where does the plus charge go? To the oxygen. So that's the resonance structure. Does that make sense? And so you can get this alpha cleavage because it's the heteroatom. If that was a nitrogen, it would at least have one molecule. With sulfur, it has 2 molecules. So the idea is if you have a lone pair on a heteroatom next to that C+, you can now make it. And so in this case, we're going to call this an aselenium ion. The C plus, this middle species is what's called, it can be either called an acyl ion or an acyl ion. Not the most stable thing, but stable, because it can form resonance structure. I mean, the oxygen is not happy with the plus charge, but then again, the carbon's not necessarily happy with not having a full charge. So fortunately, the real structure is the resonance hybrid. So that's how we do it. Carbonyls, like ketones, do alpha cleavage. And so in this case, you can probably guess what the 57 peak is. Well, if it's me, I go, okay, 86 minus 57 is, it's not 15, it's going to be 29. And so 29 is the loss of an ethyl group. And that's what I did. I lost an ethyl group when I did my alpha cleavage. So there's my acyl line at 57. Well, even 29 shows up. Because I'm losing the ethyl group, and when the ethyl group is a carbocation, it shows up as 29. So if I have this molecule, and I don't necessarily know what it is, if I do know that it's got a carbonyl in it, oh wait, how do I know there might be a carbonyl in it before I go to the mass spectrometer? IR. Right, so I might know that information before I do my mass spectrometry. If I know I've got a carbonyl in it, I'm going to be on the lookout for alpha cleavage. So I'd be looking for, a carbonyl compound weighing 86. When I see the loss of 29, I know it's got an ethyl group in it. When I see this as kind of the major peak in the compound, I'll say, well, that's going to be acyl. An acyl ion that weighs 57 would have that structure. Simple molecules, it's easy to produce, but not so much for complicated molecules. So that's the alpha cleavage for that ketone. Okay, let's see what's next. My guess is, it says at the top. How do we form the peak at 73? So you don't necessarily just have to have ketones to form to do alpha cleavage. You can have alpha cleavage off of a ether like this. Now, again, what's the alpha carbon? Well, it's going to be the carbon attached to the carbon attached. In other words, you got to break a bond to put the plus charge on the carbon next to the other. So my question is, where are you going to cleave that molecule to get a peak at 73? Do we know which one we want to cleave? Well, we want to cleave a bond that's attached to this carbon, right? So you want to cleave carbon, you want to cleave A, B, or C. It's going to be A. Because I can't cleave at C. Because cleaving C would cleave C and O, and I want those attached because I want the plus charge on C. So I can form the So that's the one that we don't want. So we can cleave either A or B. Have a preference? No preference. It's exactly the same. Right? It's an electrical molecule, so no preference. All right, so we cleave B. And what do I end up with? I end up with my plus charge here. Now, there is an H there that we probably shouldn't forget about. So there's my plus charge. Can I draw the resonance structure for that? I already got my C in 30 years ago. That's painful to say that. So there's my other resonance structure. So is that the most stable way to fragment it? Yes, it is. And I'm going to guess it probably weighs what? If nothing else, I know I lost 21. So in our alpha cleavage, we've got to have the carbon heteroatom intact, and I'm going to cleave something attached to that. All right, what's next? Oh, this cleavage. So, if you have more than one if you have more than one heteroatom, you're going to cleave in between them in this case. So if I cleave in between those two COHs, I'm going to get a plus charge here, and I'm going to get a plus charge there. I should draw on the other way. Left part on the left, right part on the right. Can we write the resonance structures for those two? Yes. So there would be my two resonance. You would have the ability to form the resonance structure. So what would each one of those weigh? The one on the left, how much would it weigh? $45. Do we agree with 45? I'll agree with 45. So this one weighs 45. What's the other one weigh? $31? I think I agree with that. Now, look at the spectrum. The spectrum has this much 45 and this much 31. Which one's more stable? 45 because it's more abundant. So when that molecule cleaves, again, remember it goes into If when it forms its dot plus, it's going to cleave into a plus dot. So which carbocation is more stable? The one at 45, which corresponded to the one at 45. Why is that more stable? Because it's a secondary carbocation in that resonance structure. It forms a secondary carbocation in one of the resonance structures. The secondary versus what is the other one form? Primary. So where it says we'll cleave with the more substituted carbon to form the more stable carbocation. Notice that the mass spectrum, this would be evidence that secondary carbocations are more stable than primary. I hope it's not going to violate any of our rules that we learned last semester, and we're going to be in big trouble. So if you want to say, well, how do people know that? Mass spectrum is a great way of showing the stability of the different carbocations. Because it's got a fragment that forms a more stable carbocation. Now the next one I think is going to be a little more fun from the standpoint of, let me do the same thing with a nitrogen on one side and an oxygen on the other. So if I do that, I'm going to compare this carbocation to this carbocation. Let me stop right here and take a poll. So given those two carbocations, which one do you think right at the moment is more stable? Let's see, the answer is not. What do you think? How many people say that the nitrogen carbocation is going to be more stable? The oxygen one's going to be more stable. Everybody else? Don't know? So that statement then about it's going to form resonance stabilized carbocations according to the electronegativities of the element. Do exactly what I just did for the other OH. Write the two resonance structures of those two carbocations. Determine their masses. Look at the spectrum and see which one is more abundant. And that'll tell you which one's more stable. And then I'm going to ask why. Is that the periodic table? Which one of the doors do I find still on the wall right? I didn't say it was a big one. I said. Remember, your periodic table will go CNOF. Have we done the first part yet? So we have the two resonance structures. Okay, so there's our resonance structures forming again, the double bond from the lone pairs on the oxygen and the nitrogen respectively. And then the nitrogen and the oxygen get a plus charge. Oh, what's the nitrogen one way? 30? What's the oxygen one way? 31? Which one is more stable? Nitrogen. Why? Okay, so the nitrogen doesn't take the positive charge as much as the oxygen. Right? I'm going to follow that up with the question, why doesn't it take the positive charge as much as the oxygen? Because it's not as electronegative. So, if we went back to judge resonance structures back to last semester, I don't remember if we necessarily did that in our class because we're all caught up with initially. But remember that if you're looking at resonance structures and you're going to compare which one to the table, the first criteria is do they both have all octets? That's the first criteria. If one has all octets and the other one's missing an octet, then the missing octet will be listed. But if we have a tie, then we go to the next one, which is we want small numbers, small formal charges, or small numbers of formal charges. Meaning a single +1 or -1 will be best. +2, +3, usually that. If we have a tiebreaker there, what do we do? We then go and say that the charges should be in a line, but should be aligned with the electron. So nitrogen is going to be more tolerant of a positive charge than oxygen will be because nitrogen is less electronegative. You want to say it the other way, the more electronegative element is not going to want the positive charge. The less electronegative element will. So did I lie when I told you that last semester? No. We have evidence here. This is huge evidence. Because given the choice, that molecule will fragment and form 10 plus. And very little with no plus. So this is a molecule that, again, the goal here is, okay, can we write our resonance structure of our alpha cleavage? When we do that, and we have a comparison between nitrogen and oxygen, and we say which one's going to be more stable, we could figure that out from that rule, and that's real experimental data that shows that's correct. Does that make sense? Is all this kind of making sense? In terms of the resonance structures, in terms of the alpha, putting the plus charge on the carbon next to the oxygen and drawing the resonance structures that way. I'm using this in the context of mass spectrometry, but my goal is also that it helps remember carbocations. So hopefully it helps that way. And I know in my lab, well, I don't know if I can say this universally, but in my lecture class, I will say, well, in my lab class, we talked about this. Where I may call on people that are involved to say, what do you, I won't do that because that'll be disastrous. All right, last fragmentation. The last fragmentation is what's called a McLafferty rearrangement. Or I believe Fred McLafferty, one of the schools. So, a McLafferty rearrangement only really occurs if your ketone or your ester can form a 6-membered ring. So here is basically this is got a isophenol group on this side. But if I take and put the hydrogen in here, I've got a 6-membered ring. And so the electrons move this way, and it's a pair of electrons moving. So what I end up doing is, if I rewrite that molecule, what I'm going to do is I'm going to break the CH bond, and I'm also going to break that CC bond. And I'm going to make 2 fragments. So if I write those 2 fragments out, they're going to look like this. And so when I break that apart into those 2 fragments, either one of those 2 fragments could be a carbocation. Or they could be a fragment. I'm getting a sense of deja vu with that. On the right-hand molecule. What is that called? We saw that molecule in the triple bond chapter. It's an enol. It's called an enol because it's half alkene, half alcohol. Is it stable? No, it's not stable. So what it does is the pair of electrons moves here, and then that pair of electrons moves to bond the carbon to the hydrogen. Remember, that is an equilibrium. That's an equilibrium reaction. So that what I end up doing is I end up bonding the hydrogen there. I'm going to put a square around it, and then I get my double bond. So I end up forming a ketone. Do you remember what that process is called? Tautomerization. So that's a tautomerization. So you want to watch out for the this is when you add H plus and water, you end up forming the alkene. So this is a major fragmentation pattern for ketones or esters that can put their groups into that 6-member ring. So it's something that I would look for if I knew the structure of that ketone or the second case again. So in the ester case, what I'm going to do is I'm going to break this bond. And so if I break that bond, and I'm going to break the CH bond, because the hydrogen is moving over to the other molecule. If I do that, then I'm going to end up, in this case, with that fragment And I'm going to end up with that fragment. Those two fragments. And so I'm going to end up with an alkene and if I started with this. So again, I might look for those fragments. Just to make sure that the McLaughlin is rearranged. So, in your homework problems, what I've done is I've given you a mass spec, indicated what the molecular weight is, and then asked you to draw the fragments that give you a particular fragment molecular weights. And so everything that I've done, we've done, is in that homework. Not not everything, but in homework is something where it asks you for the most stable. Make sure that, if there's a tertiary that can be drawn, that will take precedence over secondary. It would ask for resonance structures. We've got a couple types of resonance structures, the alpha, the heteroatom resonance structure, and we also have the allo resonance structure. So that's what I'm asking for. And all highly saturated lab and space video. I can put the summer video on, but you would care about that. Now, to end mass spectrometry, you might say, I don't really know this. I didn't know that you get that fragment. And I don't know, people just don't argue with you about it. So if you propose that, it's accepted, nobody tries to destroy your theory. That's the way science works, everybody does. Nobody's trying to destroy your theory. So how could you determine what a fragment looks like? What's its structure? Well, this is the same technique that if you go have a drug test for whatever, they're going to actually test the metabolites of that drug that's in your probably urine. And it's not just enough when they're doing drug testing to find the metabolite by saying, oh, that metabolite will come off the GC or the liquid chromatography instrument at 10 minutes and it has this mass spectrum. That's not enough. Right? They can't convict you, they can't take away your gold medal based on just that. So what they do is what's called tandem mass spectrometry. So in tandem mass spectrometry, I can choose an ion. So let's just say here's a random mass spec. Let's say that I wanted to determine what the structure of this 87 is. What I can do is, in most of these instruments, it's not really a sequential thing. In ours, all the ions are in there and they're doing figure eights in what's called an ion trap. And then the instrument ejects all but one mass of them. And so I can tell our instrument, I can say, you know what? I want everything but 87 gone. And so now I have a mass spec full of 87 fragments. Then I can impact it, and I can feed it and determine what its fragments are. And so in tandem mass spectrometry that they use for drug testing, you not only have to find the peak at that time and it has to have the same mass spectrum, a fragment or more than one fragment has to produce the same mass spectrum when it hits this point. And then it's considered a positive. And we could use that to try and figure out different structures. So if I wanted to know what the 87 peak is, I'd love to have a mass spectrum of that. Well, on an instrument like we have, we can do it. I can tell the computer, I want 87. And then I can destroy 87. And then I can look at its fragments, and if I said, well, that should be this piece should fragment to be this piece, these pieces. In drug testing, it's all done by using authentic samples. So that's called piano mass spectrometry. It's tough. I think there's only 2 years for heavy instrument probably. Probably like 7 years for mid-front. The thing that's not easy about it is I got very few 87s to work with. And then when we smash them, I got even less time. And then if you want to choose one of those and smash it, you're down to where you're like detecting 4 ions. You've lost all your ions basically. You keep taking out the wrong ones. So I think that's the problem. Because I got it down to where I'm like, I can't see anything because of so that's actually the mass spectrometry used for a lot of things. But in drug testing, they have the portable mass specs that they do in the Olympics. They'll have like, in the Olympics, they set up a whole mass spectrum lab that they're testing people. Then people using masking agents to try to cover up that peak so that it doesn't get the same mass spectrum, so that it's like, oh, it's not there. So there's like masking agents and people like that drug tests. But that's how the drug testing is like. So if anybody was like, well, I don't really think that's the peak. I don't know if anybody's done that, but you could actually go in and verify it. Or at least come up with the fragmentation patterns, what you expect. I don't know how many people have done that. We were looking at one molecule, I found one sat that had which is pretty good.
That's the breathalyzer.
No, a breathalyzer is like alcohol, some high oxide, but you cannot do that by that would be the urban legend around that is that copper will cause the alcohol to oxidize. So when you check the alcohol, it's really check what that acid. Like that, even the smaller things. If you go to New York, which that is actually more expensive than having the Dawn Spring. So that's mass spectrometry. And we use a little bit of it, but those are big deals. Okay, so we have one more lecture part today. So let's start back up again at 3:15, and it won't take more than, I can't even guess how long time. We got one more. We got one more left.
Oops.